Hi, in this module, we'll talk more about deep segmentation of images. That is, not just classifying and detecting objects of various classes in the images, but actually understanding what object every pixel in the image belongs to. Let's try to understand a bit better what we are trying to achieve here. In this module, we're going to build upon the concepts we discussed previously and introduce how we can leverage them to perform deep segmentation of images to help us with the problem of scene understanding. We'll introduce traditional superpixel approaches and CNN-based approaches and learn how we can use transfer learning to greatly improve the accuracy of our results. We've also discussed the various applications for object classification and detection. They range from detection of roads, lanes, cars and pedestrians for autonomous driving, to visual representations of the interior of the body for clinical analysis and medical intervention. In general terms, this is all part of a family of tasks called scene understanding. The ultimate goals of scene understanding are recognizing what the objects in a scene or picture are and recognizing where these objects are. But how do we represent where they are? We've already seen we can use bounding boxes for this type of problem. But if you think about it, bounding boxes are crude approximations for object locations. Usually, many of the pixels in the bounding box do not lie on the object of interest. What if we want to do better? What if we could provide tight bounding masks for the object and not just bounding boxes? To understand the scene in more detail than the functionality provided by classification and detection, we need more detailed pixel-level segmentation. There are a number of types. Semantic segmentation is about understanding, at a pixel level, what class of object each pixel belongs to. For example, the pixels for all of the fruit in an image. Instance segmentation is a step more advanced than semantic segmentation, where we know at an object instance level where the pixels of each individual object are located. For example, where exactly each individual piece of fruit is located in the bowl. Panoptic segmentation is a recently coined term for a unified view of both, where each pixel of an image is assigned not only a semantic type, but also an instance identifier. Pixels with the same type and identifier belong to the same object. Pixels with the same type but different identifiers belong to the same class of object, but different object instances. Pixels with different types are different types of things. Earlier in the course, we looked at various techniques used in computer vision to segment images prior to deep learning taking over. As they did for object classification and detection, CNNs have proven enormously successful at deep scene labeling. Traditional methods have had success in separating out classes of images from each other, using superpixels and a sequence modeling learning algorithm called conditional random fields, or CRFs. Without diving into the underlying math, CRFs estimate the conditional distribution of a sequence of labels given a set sequence of observations. They are used in this context to model pixel dependencies. That is, they capture spatial context information, essentially which sets of pixels belong together. CRFs have been widely applied to image segmentation problems. Most traditional methods cannot easily separate different object instances. We'll see in later videos that CNN-based approaches are able to resolve such issues. We'll look at fully convolutional approaches to semantic segmentation. The outputs this time are not probability scores and bounding boxes, but either a set of per-class binary masks the same size as the input image, which have ones for locations where the pixels belong to the object and zeros elsewhere, or a set of per-class probability distribution masks, again the same size as the input image, with values between 0 and 1, telling us the likelihood of whether each pixel belongs to that class or not. We can then make a decision on these probability distribution masks that values above a certain confidence threshold correspond to a yes and values below correspond to a no, and we can use these to generate equivalent binary masks. And we train the network in the usual manner, calculating our loss function or error metric and back propagating the error gradient through the network, adjusting our weights. Our loss function is now a similarity coefficient between the original reference truth masks and the predicted masks, called a Sorensen dice coefficient. This coefficient represents the ratio of overlapped regions between the segmented region and the truth regions in the range of 0 to 1. We'll also see how the output from CNN-based approaches can sometimes be blurry, and how CRFs can help improve this by bringing global contextual information into play. Finally, we'll learn how to use transfer learning to take training performed for classification problems and reapply it as a pre-training set for our segmentation problem.